Hey everyone, another day and well, not another LeetCode problem. So I figured I should probably start segregating my videos into topics, and I figured why not start a graphs playlist. So yeah, this is going to be an introductory kind of lecture on graphs. So if you're somebody who's already good at DSA and knows everything about graphs, you can feel free to skip this one. But if you kind of want to revise on the basic topics again, we're just going to go through like some jargon when it comes to graphs and like basic notations and stuff like that. So, all right. So a graph is basically a data structure which is used to represent relationships. So if we look at the main components within a graph, it consists of nodes and edges. And what nodes or like vertices are, as we can see here, there's A, B, and C. So these are nodes, and or we can call them entities as well. So whatever connects these nodes together, those are actually the edges, the connections between them. Yeah, and when we're talking about types of graphs, as mentioned here, we have two different types. So the first one over here is an undirected graph. It's cyclic here because everything is connected together. So as we can see here in the first one, there's no direction, but they're all still connected. And the second type is a directed graph. So I've just mentioned the cycle part over here, but it's basically directed and undirected. So this is a directed acyclic graph here because as we can see, A can connect to B, and D can connect to C, C to B, and A to D, but B can't really connect to other nodes. So we see there is no cycle here. So yeah, that's that. And then we have two types of edges, which is unweighted and weighted, and it's pretty self-explanatory. So if those edges actually have weights, then they're weighted, or else they're unweighted. Okay, so now talking about the representation style of a graph. If you're looking at your problems on LeetCode or any DSA problems, the way a graph is normally given is either in the form of an adjacency list or an adjacency matrix. So if we look at the graph over here and we look at the adjacency list, then we can see because A is pointing towards B and then A is pointing towards C. So we have B and C in the neighbor of the node A. And B doesn't really point towards anything, so it can't really traverse to any other node. So that's empty. C connects to B, and then D connects to A and C. So we see that. And in the adjacency matrix, it's basically the same thing, but we're just using like index values here to represent these nodes and the way they're connected. So A is connected to B and C. B is connected to nothing here, C is connected to B, and then D is connected to A and C. So that's the same thing. And yeah, graphs are basically everywhere, like social networks or maps, cities, roads, actually physical networks as well. So network connections, internet connections, all of that. So everything is, it's a graph. Okay, so what's a path? So it's a sequence of vertices connected by edges. So you have some nodes and those nodes being connected to each other. And yeah, so this itself is a path. So as we can see here, A to B, B to C, C to D, that itself is given, and that's a path. And the length of the path is the number of edges in the path. So the length over here is 1, 2, 3. So L is equal to 3. Because you basically took 3 steps to get to the last node here. Okay, and so cycle is when you start at one node and then you end back at the same node. So if I were to draw another edge over here and D was connecting back to A, then we could have said that there was a cycle. So yeah, starting and ending at the same node. Okay, now we can talk about degrees of a node. So when we're talking about an undirected graph, the degrees of the node are basically the number of edges connected to that specific node here. So if I want to look at node B, the degree of B is, it's only connected by one edge. So degree of B would be equal to 1. As I can see, A is connected 3 here, so degree of A would be 3. And same way as degree of C would be 2. And degree of D would also be equal to 2. So yeah, it's just basically the edges that it's connecting to other nodes via. And when we talk about a directed graph, so in directed graph, we have two types of edges. So this can be an in degree or an out degree edge. And basically what that means is an in degree is like edges that are coming towards that node, and an out degree is edges that are going away from the node. So if I look at B, nothing is actually heading towards B here. So the in degree of B is equal to 0, and the out degree of B, as I can see, sorry, I was wrong over there. My arrow is pointing here, sorry. So the in degree of B is actually 1 because A heads towards 1, A heads towards B. And then the out degree of B is at 0. Yeah, and if we want to check the in degree of A over here, we see that D is pointing towards A, so that's 1. And then out degree of A is actually equal to 1, 2. Yeah, so I guess you guys get the idea. So let's talk about total degree property. So it's stated that in any graph, the sum of all degrees is equal to twice the number of edges. And if you think about it, that's actually very intuitive because you have a number of nodes and then each edge actually connects two nodes together. At max, one edge can only connect two nodes together. So that is contributing a degree to both of these nodes. So once you sum it up together, you will get twice the number of edges, has to be the total number of degrees. So if I look at this, I see A has 2 edges, B has 2 edges, C has 2 edges, and D has only 1 edge. So I've kind of written that over here. And if I sum all of this together, it's 4, 4, and that's 8. And as we can see, the number of edges is equal to 4, and 8 is 2 times 4. So yeah, that property holds good. Okay, now let's talk about a connected graph. So a graph is considered connected if every node is reachable from every other node. So as we can see here, A, B, and C, they're all connected and it's undirected. So basically everything is reachable from every other node. It's connected. And if we look at this over here, this is a graph, but we happen to have like different parts over here, and we can see that this ABC connection cannot reach D and E. So in this case, or even in this case, we're ABC, so A can go to B, B can go to C, but C cannot go back to A. So that's it's unconnected over here. So if there was a connection here, it would have become a connected graph. All right, so components, connected component. So a connected component is basically a group of nodes which are connected to each other. So in this example over here, this is one connected component, and then this is another connected component. So yeah, there is no connection between them, so they're two different components. Okay, so now the terms dense and sparse, as the name suggests. So a dense graph is one that has like multiple edges in it, and a sparse graph would be one which is very simple and has relatively very few edges. Okay, so now we can talk about the traversal techniques for graphs. So there are two main traversal techniques. One is breadth first search, and the next one is depth first search. So what happens in breadth first search is we go level by level by level, and in depth first search, we go to one node, we go to the extreme depths of that node, and then we come back and then go to its next neighbor. So we continue doing this. So yeah, let's check out what happens in breadth first search. So if I am to start here, and if you're implementing this, at least in Python, so you're going to use a queue, a DQ. You're going to have a visited set. So you make sure that you don't go and repeat somewhere again, because that's redundant work and you might get stuck in a cycle if you do that. And if you're trying to print it out or something, then you have like a BFS list or something where you're going to add those nodes in the order of their occurrence. Okay, so what happens here is we look at A. So let's say I do have a queue and I do add the value A here. And then I'm going to look at the neighbors. So I'll probably do my BFS list as well. So the first thing that would get added here is A. And then I would look at the neighbors of A. That's B and C. Okay, so I'm going to add B and C. And this time I've actually, I've traversed A already. So I'm going to pop that out. Then I'm going to look at B. So I look at the neighbors of B, that is D and C. I go ahead here, add D and C. And I sort of forgot to have like a visited set over here. So A is visited. I'm gonna add that over there. Now I've come to B, so B is also visited. And then I've added, okay. Okay, I wasn't supposed to add C over here. Can I remove that? Okay, what happened? B and C were actually, oh, all right. I have named it wrongly. This should be an F. Okay. So I came to A, my neighbors were B and C. And then once I came to B, my neighbors are actually D and F. So I add those. And next time when I come to the queue and I pop from left, the value is actually C, which had to be removed. So once I remove C, I'm going to look at the neighbors of C. So I'm going to go ahead and add E. And now visited, C is added, BFS list, B was added, C is added. And next I pop from the queue is D. So once I remove D, I want to add that to the list, also to my visited. And so the neighbor of D, it doesn't really have any outgoing edges here. So I'll go to F, okay? So I want to go ahead and add that to my BFS list, also to my visited. And I want to check, so the neighbors of F is actually D, but as I see, D is already visited, so I'm not going to add it again. I can pop out E, and E does not really have any outgoing edges. Let's just say it was like this. So it doesn't really have any outgoing edges, so I'll just add that to my list and add that here. So if we do this, this is what we get. We get like this traversal path, and we were able to do like a layer by layer traversal of it. So that's breadth first search. If I had to take the same thing again, like A, B, let's like C, D, maybe like an E over here or something. That sounds okay. An E and maybe like an F. Maybe something like this. Okay. So what I would do in this case is if I start from A, I'm not just going to go level by level. I'm going to go to the neighbor of A, yes. So that's B. And once I go from A to B, I'm going to directly look at the neighbor of B. So in this case, it's D and C. So what would happen is, so it would be neighbor is like D and neighbor is C. So let's say I initially go to D and I want to go to the depth of it, right? So from D, I would go to, I would actually go to C. So again, we'd put that in the visited set, and we wouldn't have to go through this again. So I'd go to C. And yeah, after I finish this, that's when I come back to A and look at its other neighbor here. So that would be E, and then E would go to F. So you guys get the idea. We traverse the depth of it first, and then we look at the next neighbor. So it's not level by level. So that's depth first search. Okay, so when we see BFS or either DFS, when we want to consider the time complexity. So what's happening? We're going through n different nodes. So that's O of n here, and we're also traversing all of their degrees, right? So the sum of degrees, as we talked about earlier, is basically 2 times the number of edges. So that's the time complexity for both BFS and DFS. And the space complexity is, so what are we using? So we're using a queue when it comes to BFS, or either the recursive stack when it comes to DFS. So we have a visited set, and this is optional if we're using like an output list. So if you add all that together, it's 3n, which is basically O of n. So yeah, and you can remove this 2 here. You can just remove the 2. So n is also represented as v for vertices. So it's O of v plus e, and this is just, it's the same as O of v. So yeah, that's all I had planned for this video, at least. So I hope this was a good enough explanation of the basic stuff as well. So yeah, I'll be going through some problems after this video, and I hope you guys like it, and I hope it's helpful. So happy coding.